Good evening. Can you hear me?
Yes.
Hooray. Thank you all so much for your patience tonight. I'm sorry that we had some technical difficulties. It figures the talk that I'm most excited about is the one that would have the most obstacles. So we got here. Thank you again for your patience. My name is Christine Muir. I'm the community librarian here at Cary Library. Part of my job is to plan and host events like tonight's, which is one I'm really excited about now that the tech works, knock on wood. Please take a minute to silence your cell phones so we don't interrupt our presentation. If anyone needs an assistive listening device, I can pull them out, although I'm not sure they'll work given the way our technology is set up. So let me know if you have trouble hearing things, and we'll find another workaround for that too. It's the most troubleshooting I've ever done. We always like to thank the donors to the Cary Library Foundation for supporting all of the programming efforts at the library. There will be time for audience questions after the presentation tonight. I will run a microphone around. The speaker will not be able to hear your questions unless we have a microphone. Given that we've jerry-rigged things, I will either bring you a microphone or I'll come listen to your question and repeat it to the speaker and she'll repeat it. We'll figure it out as we go. So if you want to ask a question, just raise your hand and then wait for me to come to you, please. Tonight's program on the James Webb Space Telescope is part of the Cary series on science and economics. It is my distinct honor and pleasure to work with Mr. George Burnell in bringing you these programs, which always offer fascinating speakers on a variety of topics. And if you're interested in signing up to hear more about these programs as they get planned, we do have a sign-up sheet, which is good old-fashioned paper and pen, so we know you can get on that list tonight if you want to. This is our second year of offering these programs, which have always been very, very interesting, like I said, and on a lot of different topics. And it's all about what your neighbors are doing. So there's a really strong community connection, which also makes it a really interesting and fun project to be part of. Please join me in welcoming Mr. Burnell to the stage to introduce tonight's speaker.
Thank you. This is about NASA, but this is not Houston, as you can tell. Welcome to the Science and Economics series at Cary Library. This email list, if you want to be notified, is my list. It stays private with me. Our speaker this evening, Dr. Kathryn Flanagan, is a senior scientist at the Space Telescope Science Institute. The Institute is responsible for the science operations of the Hubble Space Telescope, as well as the mission and science operation of its successor, the James Webb Space Telescope. Dr. Flanagan has served as mission head of the James Webb as well as deputy director and interim director of the Institute. Dr. Flanagan came to the Institute in 2007 to head the mission office with responsibility for establishing the James Webb Science and Operations Center. She earned her PhD in physics at MIT, where she began working in the field of X-ray astronomy, with special interest in developing new instruments for space, and has worked on multiple flight instruments. She has participated in NASA's advisory structure, co-chairing strategic planning documents, and serving on advisory committees. She has been active in education, beginning with service as a Peace Corps volunteer, teaching math and physics in the Democratic Republic of the Congo, and is a strong advocate for science outreach to the public and the next generation. Please welcome your neighbor and mine, Dr. Kathryn Flanagan.
Thank you all. Actually, I think what I'll start with has nothing to do with James Webb. It actually is this title slide. It's basically filler while we're all sitting down. But while I was interim director, it was the Hubble 25th anniversary. Things were going crazy. We had some images in the can ready to go for a press release, but one of them didn't turn out to be a winner. Sorry, can't hear me. Okay. So with director's discretionary time, I was able to take a backup image, which is actually this one, the Veil Nebula, which is a supernova remnant. About 8,000 years ago, a massive star, 20 times more massive than our sun, blew up in our galaxy and was witnessed by our ancestors 8,000 years ago. So I did the obvious. I looked up what else was going on then, right? Come to find out, that was a good millennium, all right? So, the earliest recorded domestication, not recorded, but the earliest domestication of the cat. For those of us who are not allergic, that's a good thing. Proto-writing started in China and 2 other locations on the Earth. And the third, and my favorite, was cultivation of barley, which gives us beer, and a supernova. Okay? So that was a great millennium, but actually, the one we're living in now, as you're going to see, is pretty thrilling too. We got some other inventions ahead of us and some technologies going. So let's see what's going on. Okay, I'm going to talk about the James Webb Space Telescope. You're out in space in this picture, well beyond the moon, and there's something coming your way. I see that the moon moved out of the way, and there's the sun blinding me, and here comes James Webb, which, by the way, is going to be launched and reside much farther away than the moon. Much. Okay, so that's what it looks like. Maybe it doesn't look like a big deal, but together we'll actually design how it should go and what it should do together. And we will know why it looks this way. So this is actually, when I say audacious, I mean it. It's the biggest astrophysics mission, space mission, that NASA Astrophysics will ever have launched up till now, okay? As you will see, it is so large that it has to be folded up and jammed in a rocket. So, it's international. On all these big ideas these days in science, we all partner together to get the job done. As you can see, we've got NASA, we've got the European Space Agency, or ESA, the Canadian Space Agency. There's your iconic, soon-to-be iconic mission. Goddard Space Flight Center is our NASA center that manages us. Northrop Grumman, we partner with industry. That's what we call the prime contractor. And I work for the Space Telescope Science Institute. We're going to operate that thing once it launches, which means it's all on us at that point. All right, this thing is actually a lot larger than this little image would appear. The mirror itself, which as you can see is segmented, is 21 feet across. Several stories just for the mirror. The whole shooting match is something like 3 stories high. I'll show you a full-scale image. It's so large, it will be folded up and launched on an ESA Ariane 5 rocket, which is designed to be able to lift something that large and massive. But even so, we had to fold it. They call it the origami telescope. The goal is 10-year mission. Lead is NASA Goddard. I've told you about the international collaborators. And there are 4 instruments. We'll have more about this later. I won't touch on this very much, but we have university involvement, University of Arizona and Lockheed Martin for NIRCam. This is an American instrument. the near-infrared spectrograph, ESA and Airbus, European Space Agency. This is actually close to my heart and arguably the most complex instrument, the first of its kind ever to launch in space. The Mid-Infrared Instrument, or MIRI, the European Consortium. MIRI is actually going to go to mid-infrared wavelengths and show us a window of the sky that we don't have access to right now. And NIRIS, which is the Canadian Space Agency, the Near-Infrared Imager and Slitless Spectrograph. I won't talk about this too much, but I just want to introduce it. Okay, there are 4 science themes, 4 great pillars that drive the design of this mission. And we'll just choose one of them around which we're going to create our design. The top 2, first light, the desire is to actually see, measure, observe, get images and spectra from the very first galaxies ever to form in the universe. The first. Pretty good. It's called First Light, and this has been nicknamed the First Light Machine. We're going to design it around this one. If you can see the first galaxies to form, that means you can see the galaxies that are younger or that have come more recently than that. So you can actually take pictures of galaxies from the beginning all the way up through until now, and we'll take a look at what some of those look like. That means you can actually see galaxies evolve with time, in principle, by looking at a number statistically. And this entire first line of themes has to do with what I'm going to call redshift, and we'll get to that later. The second one has to do basically with skewering dust. You know, one man's dust is another person's radiation. Well, lots of great things go on in dusty environments. Stars are born there, planets are born there. Oh, if we could only see into the dust. Well, this machine is designed to do that, so it's going to allow us to see the formation of planets around stars other than the sun, that which we call exoplanets, which is a very interesting prospect. So the Earth ain't the only planet around, it turns out, and we may be interested in understanding the other ones. All right, so let's see where we go next.
Our whole universe was in a hot, dense state that nearly 14 million years ago expansion started. Wait.
This is information we need to design. Our whole universe started in a hot, dense state. Okay, that's great. We are going to design an observatory to see the first galaxies. That's our goal. We'll do that in this room. But we need a little information. Okay, so the universe started with a hot, dense state, looking good, no galaxies yet, about 14 billion years ago. Okay, so now we know about the time frame, about 14 billion years. Now, it turns out the universe didn't actually start with galaxies. It started with stuff, energy density, gets particles, gets stars and galaxies forming eventually, and eventually the light gets through so we can see. Those are the ones we're going to see. Okay, so we're going to look back maybe not 13.7 billion years, which is the age of the universe. We're going to look back maybe 13.5 billion or 13 billion. So that's our goal. We're going to try to look at an object formed 13 billion years ago. Okay, good. We've got some information. Now, made a start. Let's talk about light real quickly. This is the light that we see, visible light. It's just a little patch, actually, of the whole spectrum of light. Light is a wave, sometimes. If you go to longer wavelengths in this direction, you see infrared. Remember the infrared. We're going to come back to that one. Microwave, radio, real useful. And if you see shorter wavelengths, you get gamma ray, X-ray, ultraviolet. X-ray is what you get when you actually go to the doctor. You're illuminated with X-rays. Chandra is an X-ray observatory operated in Cambridge, right down the street. But our eyes see visible, and it's really convenient that it does, because galaxies and stars, we see them, which tells me galaxies and stars radiate visible light. That's another piece of data we're going to need. And they also radiate ultraviolet light, just so you know. Now, we don't actually see infrared ourselves, but it turns out snakes do. There are animals that see infrared. It's useful to them, and we'll figure out why later. They can actually just find prey by the ability to track with the infrared. How might that be? Okay, so we're going to think a little bit about light, because with the universe, you can't perform an experiment on it. You got to observe it and then figure it out. So the only way for us to observe a galaxy that's 13 billion years ago is to look at the light that came from it. So we have to think about light. So we know we're going to look, let's think about this. Let's go to the next one. Okay, here's our problem. Design a machine to see the farthest galaxies, the first galaxies. So the first question was when? About 13 billion to 14 billion years ago. And the next question is, how far away do we have to see them? Well, if that light was emitted 13 billion years ago and arrives today, October 22nd, then it's been traveling for 13 billion years, which means it's traveled 13 billion light years. A light year is the distance light travels in a year. So I gotta look 13 billion light years away, which is actually kind of close to wherever the edge of the universe is, okay? So I have to look far. So my first design criterion then is gonna be faint, all right? So whatever happens, I'm gonna need a big mirror to capture enough light. So our first design that we figured out is a big mirror. We're 90% of the way. Well, 30% of the way. Okay, so what's the next step? All right, we're well on our way. Okay, next step, I keep pointing in the wrong direction. And I remember, if I see a galaxy as it first formed, I can see all the ones in between. So this is a good sign. All right, what kind of light should I observe? Do I make a normal telescope? Better think about that one because it may not be correct. All right, this is the galaxy I would like to observe, and I'm seated. No, this is the one I want to observe, and this is me sitting there with my satellite, hoping to observe it with a telescope. And the light was emitted by my distant galaxy, and it was emitted in visible and ultraviolet like any other galaxy, except for one little thing. The universe was expanding. In the meantime, 13 billion years, the universe was expanding, so the wavelength got stretched. And when you have a longer wavelength, you have red or infrared or microwave or radio instead of visible. So it's red shifted. So the light, which is normally visible light, gets detected as infrared light when our telescope captures it. So we now have the second design criterion. Big mirror, infrared sensitive. Just about done, right? Okay, I got one more thing I got to think about though. You know how you try to look at, let's say, the Milky Way galaxy or the night sky? It's a terrible job trying to see it from Newbury Street. It's so much easier from Maine or New Hampshire. It's because of that, well, light pollution, frankly. It depends if you're an astronomer, it's light pollution, and it's the city lights and lovely, depending on your perspective. Okay, so I'm seeing something faint, 13 billion light years away. Am I gonna have light pollution? Well, visible light isn't infrared, so maybe it doesn't matter, right? I'm gonna make it infrared sensitive with infrared detectors. That might not be a problem, maybe. But wait a minute, let me think about this for a second. That's an infrared video of a dog. Now, if Ginger, sitting on my lap at just the right temperature, shines in the infrared, maybe Ginger could give me some light pollution, right? In fact, I looked up the temperature of the Earth, and I did the calculation, and you know what? It radiates black body radiation at 10 microns, dead in the center of where I hope to detect. So I like this planet, I've chosen it for my home, but quite frankly, light pollution, infrared, it's radiating like mad. Okay, so our third design criterion is we're gonna have to shield our observatory, our mirrors, from the light pollution from the Earth and the moon and Ginger, and probably the sun. We should just, just take care of it, right? Just do it. So we're gonna need probably some kind of umbrella, some kind of sun shield. All right, we got 3 criteria: sun shield, a big mirror, and infrared. But if I have a sun shield, I gotta make sure it's always in the way of the Earth, that it's always blocking the Earth and the moon and the sun. How am I gonna make sure it's always, always, always angled just right? Fourth criterion. We got a big mirror, we got infrared sensitivity, we want it shielded from the light. Here's the fourth trick. We are going to put it in a gravitationally favored spot. It's called L2, the second Lagrange point. Its magic is that the sun, the Earth, and the moon all stay in a line with L2. If you stick something at L2, L2 moves around as the Earth moves around the sun. As long as it resides at L2, its centrifugal force gets balanced with gravity. All is good. All these things line up. That means if I put a sun shield there, like this, all that light pollution stays on the other side of my umbrella. Awesome. Okay, we have our design. We have our design, and we did it right here. So now we know. This is going to talk to us about L2, I think.
Earth. But 1 million miles further out, beyond the moon. The telescope's mirror is perpendicular to the 70-foot sun shield, which keeps it cool.
Okay, so we keep the optic, and I will point out the instruments are hidden here. All of that is going to be on the shady side of our parasol of our sun shield. So we're good, but it is 1 million miles away. And I would like to mention, although that real estate is getting more expensive every day, the real problem with it is our observatory is going to have to be at 40 degrees Kelvin. 40 degrees above absolute zero. We are talking cold. Liquid nitrogen temperatures is a balmy day at the beach, okay? So the design is going to be challenging. So we just have to remember that's another complication. But we have our design, we know what we're doing, we are going to see the first galaxies. Okay, it's big though. It's actually too big at the moment to be launched whole. So we broke up the mirrors into these hexagonal segments and we folded it up. And we took the sun shield and folded that up like a cocoon, jammed it into the rocket, and it's going to be launched from a European launching station in French Guiana in, I hope, March 30th, 2021. Okay, so let's take a look. Probably, there it is. Here's how Webb, once it's released, will deploy itself. Notice, we're showing the location. It's gone beyond the Hubble orbit, communication satellite orbit. It's now going beyond the moon. What drops down first are the solar arrays to get power. There's no sound on this one, so it's good. Yeah. We drop down the antenna. We are now about to tension the sun shield. There are 5 of them. It's not overkill. Now they're being separated, 5 of them. The reason we have 5, there are a bunch of reasons, but one of them is because if you have a micrometeorite come through it, you don't want a direct light path all the way. Now the secondary comes down, flips down, and the sides of the mirror come in place. We're only 14 days into the launch. Now it looks like the James Webb that we designed. And about 1 month in, it arrives at L2. Now, L2 is a pretty stable position, but not perfectly stable. It's a reasonable hangout, okay? But it will take some fuel and some energy to keep it obedient. So it'll be in a halo orbit around L2, but it will take some station keeping, which is why there's a lifetime of 10 years. Okay, so we have a good design. We're all set. That was easy, right? Okay, So we know we have a hot side and a cold side. On the cold side, you got to have your mirror. You got to have your instruments on your cold side. You don't want any heat because even lukewarm things give you light pollution. Your science instruments on the cold side. On the bottom, that's where you want your solar panels. They do want to see the sun. Your spacecraft, and something we call the momentum trim tab. It turns out because these are such large sun shields, they're as big as a tennis court, for those of you who play tennis, that the light pressure matters. And you gotta take that into account as part of the station keeping. Okay, so here's a full-scale model with real people who actually worked on it. This is nowhere near how many people have worked on this, but it gives you an idea of how large it actually is, which I think is pretty nice. Now, where are we? Infrared. Now we know that warmish things glow in infrared because Ginger glowed, right? But here's the thing. It's not just contaminant. It's actually an asset. We know it's going to show us redshifted light. That's a big asset. But take a look at this. The other thing is, it shines right through stuff that visible light can't penetrate. Okay? The infrared light came right through this little trash bag here. That's pretty convenient, because what that means is if I have infrared light, it will penetrate all these dusty regions and I'll be able to see right down to it. That's the second great benefit of having an infrared sensitive observatory. We are going to look into dusty, obscured regions, places we couldn't see before. So let's take a look at the kinds of things that we'll see. I'm going to show you Hubble pictures in the visible, generally speaking, and then I'm going to show you what it looks like in the infrared. And let's see just how similar they are. Here's the visible. Whoa. Here's the infrared. In the infrared, you see a star and jets coming out. Nothing like that in the visible. Who knew? That was the visible, right? I keep pointing the wrong way. And that's the infrared. Okay, let's take a look at the next one. This, I'm not a fan of this. It looks like a big dark blob, which is what it is. Very obscuring in the visible, you can't see anything. There's probably something interesting going on here. Let's see what it is in infrared. Wow, right? Completely different structure. Here's the next one. And this is part of the Orion, which has a star-forming region. I'm going to point out, here's sort of a widow's peak here that looks like it's some kind of dust column. And here's some dusty fingers here. Let's see what happens. Two things happen now in the infrared. Sorry. I seem to lose my connection. Yes. Not only, it's going to be looping, not only do we now see those obscuring regions in the mid-infrared or the near-infrared and towards as we start to move up, they actually start to glow. The things that were opaque before and in our way become transparent, and then they glow. So it's going to be a window on the universe that's really interesting to us. Okay. Now we got our four themes. We are good to go. We are going to revolutionize science here. The first two were redshift. The second two were dust. So what did the early universe look like? We're going to look at the first galaxies. They were spectacular, right? Well, let me think about this. Okay, here's a Hubble picture of an early galaxy. And it's kind of fuzzy, which you don't expect from Hubble. And you can see some structure in the background. Here's James Webb, simulation, of course, because it's not launched yet. You can start to see the spiral structure, or whatever there is, and a lot more detail in the background. For your information, interestingly enough, for the wavelength regions that Webb overlaps with Hubble, it actually should see better than Hubble, which is kind of amazing. All right, so what's the big deal with how did the early universe go? I'm gonna take a look at this Hubble ultra deep field. There we go. Sorry, I'm having technical trouble here. There, let's see if I can get this to be obedient. Yes. All right, we are now looking in the ultra-deep field, which is a boring patch of sky about as big as a straw that Hubble actually spent a month looking at. And it revolutionized the way we see the universe because it's all full of galaxies as far back as you look. So we're looking and we're looking and we're looking and we're going in deeper because we're interested in seeing how many candidates and how far we can see, and are there any really early universe, Big Bang, just after the Big Bang kind of galaxies. We're looking, and pretty soon, it'll be a little faint here. I hope you can see it because it's kind of bright. You're going to see some red circles showing up very soon. Maybe they're not red. See these circles here? These circles are showing you candidate early galaxies. You can hardly see anything in them, but if you look closely, you'll see smudgy little red dots. There. Isn't that awesome? A red dot, okay? So Hubble can see some red dots, but it wasn't designed for it. James Webb will pick them up like mad, and it will be able to image them. All right? So that's what we're looking for. That's our candidate. That's what we're hoping happens. All right. What's the second one? Galaxy evolution. We said we'd be able to see how galaxies evolved. Frankly, all the galaxies around us are gorgeous. But how did they wind up that way? You saw the blob that I saw. It's a blob. Right? Early galaxies look kind of, right? But our galaxies are, beauty's in the eye of the beholder, but still. Well, it turns out, remember, the early universe, it was close together. It has expanded. That close together probably encouraged plenty of interactions. And what you're seeing going on here are modeled interactions followed by the actual picture from Hubble of a real galaxy. So we're starting to figure out how these colliding galaxies actually interacted. And very likely, they interacted back in the day when they were all close together. And so that's probably how we got the shapes we get today. All right, so that may be a good explanation for how we have lovely grand spirals. What about the next one? How do you make a star or a planet? That was the third one. We're interested in the births of stars and planets. In the visible, you get dusty clouds you can't peer through. In the infrared, you can not only see through it, sometimes it's illuminated. So let's take a look. This is a star-forming region, and it's a model of one based on scientifically valid assumptions. If you peer into a star-forming region, you see how bright it is there? Early stars are very, large ones are infrared and very hot, and they blow channels out, so you can see the channel's been blown out here. But what you are going to see pretty shortly are, in some cases, young stars forming, and around them, something very interesting coming up. Take a look at these little tadpole shapes. You see that? Dusty Taurus, dusty hint Taurus, looking a little bit like, say, a solar system. This is how you get a planet. You get a star forming up here, and around it you get molecular clouds, dust, chunks, all those things circulating, colliding, gravitationally attracting each other, bonding together, and forming planets. So that is what we think happens when planets form. And the good news is there are like 4,000 of them we found, so we're not alone for planets in this universe. There are a lot of great ones out there that we're going to want to look at. Okay. I have no clue. Here we go. So why do we want to look at planets? We want to look at planets spectrally. We want to look at, I wonder if I think I just skipped a movie that you guys are going to need. You may not, you're going to need sound for this. Here we go. All right. This is going to explain how we're going to examine the atmospheres of exoplanets.
How do we learn about a planet's atmosphere? How do we know what's in the atmosphere of an exoplanet? The majority of known exoplanets have been discovered because they partially block the light of their host star. This is called a transit. During a transit, some of the star's light travels through the planet's atmosphere and gets absorbed. The light that survives carries information about the planet across light years of space where it reaches our telescopes. However, the planet is very small relative to the star, so it is still very difficult to detect, which is why we need a big telescope to be sure to capture this tiny bit of light. So how do we use a telescope to read transit light? Stars emit light at many wavelengths. Like a prism makes a rainbow, we can separate light into its separate wavelengths. This is called a spectrum. Visible light appears to our eyes as the colors of the rainbow, but beyond visible light, there are many wavelengths we cannot see. Now back to the transiting planet. As light is traveling through the planet's atmosphere, some wavelengths get absorbed. Which wavelengths get absorbed depends on which molecules are in the planet's atmosphere. For example, carbon monoxide molecules will capture different wavelengths than water vapor molecules. So when we look at that planet in front of the star, some of the wavelengths of the starlight will be missing, depending on which molecules are in the atmosphere of the planet. Learning about the atmospheres of other worlds is how we identify those that could potentially support life, bringing us another step closer to answering one of humanity's oldest questions. Are we alone?
So, if we could go and look at the atmospheres of planets, we would be able to detect through transit spectroscopy what elements are in there. So, these are the atmospheres, the spectral signature of the atmospheres of 3 planets in our solar system. Now, if I only had a detector that could show me the carbon dioxide line, I'd think they were all identical. And I know carbon dioxide is we breathe out carbon dioxide, so could be something breathing there, but I don't know, right? Ozone, I need ozone before I can distinguish among the 3, and I need water. I'm interested in all 3 of those to be able to tell. So let's actually examine what are these particular ones. Well, the top and bottom ones are Mars and Venus, and we're not familiar with too much life there. But the middle one is Earth. So if I were able to look at the spectrum in several key signatures, I might actually be able to tease out an Earth-like planet from another type of planet, which would be very interesting. All right, so what makes a habitable planet? Because let's face it, that would actually be pretty good. Finding a habitable, maybe even someday an inhabited planet. But, well, basically, if you look at the spectrum, this is the Earth spectrum, from reflected light from the moon, actually. And it has signatures of oxygen and ozone, the vegetation jump, water vapor, cow flatulence, methane, all kinds of things. Taken together, some of them can be formed just by lightning. Doesn't mean there's life. But the ratios of them do matter. That actually helps to tell the story. Here's a system that was discovered of 7 planets around a nearby star. We call them exoplanets. All planets around other stars are exoplanets. Of the 7 exoplanets, 3 of them are in the habitable zone. They could have liquid water. How interesting is that, right? So, and this is not all. NASA has launched Kepler, and it now has TESS, which is an MIT-led mission. These missions look at exoplanets, and Kepler has, between Kepler and other means, we found there are 4,000 exoplanets that are known, and it pretty much climbs every day. You can have an app on your phone that tells you when there's another one. And some of these are going to be great candidates for Webb to look at. Okay, however, here's the thing. Finding a planet with a star in the way is kind of difficult. All right, here's a planet. Here's something. If you could just block out the starlight, like we're about to do, put your thumb over that star in the middle, you can see the faint planets only then. But as long as that star is in the way, it's just blinding. All right? So, what we do is we actually build instruments that put a thumb in the way. They're called coronagraphs. And James Webb will have a coronagraph. Let's see how coronagraphs work. Here is the Earth, the size of the Earth, which is the kind of planet we'd like to find, compared to the sun. It's just impossible. Here is an actual Keck Telescope picture of a star that we believe to have planets. So obvious, right? Let's take a look. There's one. There's another. Oh, yeah. No question. Now, when you put the coronagraph on, those three come right out. So, James Webb has a coronagraph. I would like to mention it also is able to track moving targets, which means follow planets in the solar system. And in the end, James Webb won't get us there, but we have ideas. We might actually tackle someday the question, are we alone? So, we have designed it. We have great dreams for it. We know what we want to do. How far along are we? Okay. Let's talk about the technical progress very briefly and then wrap it up. First of all, I'm about to talk about the technology. There are several first things that JWST has done. A number of them, actually, as you can imagine, being able to come up with the technology that works at 40 degrees Kelvin. So, for example, being able to take a telescope that's folded up, launch it into space, unfold it, and then focus it mirror by mirror, and retweak it every 2 weeks. That's wavefront control, okay? Micro shutters. One of the instruments has like 10,000 little windows on it that can be opened as you see fit to look at whatever you want and get a spectrum. So there's a lot of things here. But it's important to point off that whatever technology advances you do, it's not just astronomy that finds uses for them, okay? For example, wavefront and optics of this type have obvious spin-offs into medical for improvements in laser eye surgery, measurement of human eyes, and so on. Commercial, if you're testing a mirror at just about 40 degrees Kelvin, okay, that's going to give you all kinds of other information for cryogenics. I can even tell you how we wound up the problem. We polished the mirrors at room temperature, chilled them down, and they turned into potato chips. Then we took them down to Marshall Space Flight Center and tested the potato chip shape and measured the pieces that need to come off. That's called a hit map. Then we brought it back, brought it up to room temperature, and scrubbed off the high parts. Then brought it back down, brought it to 40 degrees Kelvin, took a look, nice and flat. Done. Okay, that's what we had to do. Down below, any kind of infrared sensors. Now, I'm just saying, because I'd speculate, but I can imagine an infrared sensor would be very useful for finding hot trails of things. And cryogenic integrated circuits. As you realize, everything we launch up there has to be not only radiation hard, but in this case, has to survive cold. Okay, so without getting into it, these are the 4 instruments. I love them all. We have moving target support. As you know, we have coronography. We can look at planets within our solar system. We can actually look at complicated fields and take spectra of 100, 200, 300 at a time. Okay. Here are the mirrors in development. Lovely. Gold-coated, yes, not just for the looks. There's actual good reasons for it. That gives you a size of each hexagonal mirror. This is what the sun shield starts to look like, and the guy in the middle was the NASA administrator at the time, Charlie Bolden. And when I look at it, all I can say is, how come you're not in a clean suit? Right? You too. It makes me nervous. Okay, so next, here are some detectors. Under fabrication, now you've got the gloves on, now you're covering your face. Okay, good man. All right, next one, this one. This is actually the test chamber for the Apollo series. It's the largest one NASA has and the only one large enough to test a part of James Webb. It used to be part of their tourism circuit. They actually reclaimed it, cleaned it out, refurbished it, and then used it for the test of Webb. So what's happening here is they're about to take a mirror in. They have a complicated structure here that's going to offload the weight so it simulates a zero-G environment. And they're going to test the optics of that in this, closing the door and keeping it clean. So they had to take this tourist thing and clean it out like an operating room, basically. And there you can see the test setup. Here is the assembled mirror, starting to look real, right? These are pictures. Here's instruments. Here's the back plane, which is where the instruments get tucked. Here's the chamber again. Here's the sun shield deployed before it's been assembled. Now we got two things going on. The last two things that are recent. Here's where they were deploying the secondary to make sure it worked. This is a time-lapse actual image of the test. It says the spacecraft is not physically attached. Looks good. The next milestone, joining the telescope to the spacecraft. Now, I am pleased to report we have met the milestone. Here is the telescope attached to the spacecraft with the shields attached. So now it's assembled into one unit and released just yesterday in a press release. They deployed the sun shield in this configuration using the electronics and the commanding to see that it's going to work. So we are getting there. Now, our role, my institution, Space Telescope, they're supposed to run the mission once it launches. They're supposed to return the science, run a competed peer review. They're supposed to provide tools to be able to use these intricate instruments and training. And a very important element I'd like to mention, they need to make James Webb be a household word like Hubble is. They need to do the outreach and the education. And I just looked online to find some of the examples of how Hubble has made it into our pop culture, right? Here's a Hubble-skinned guitar. Here's a people-skinned Hubble tattoo, right? Here's actually a Hubble-themed pair of tights. I was a little bit worried that James Webb might not make it, and I want to mention it for holiday gift last year. The Veil Nebula, my supernova. So I looked online, and I'm pleased to say I found artwork based on Webb, hands coming out of the mirror. I found, very important to me, jewelry based on James Webb. So let's see what comes next. Is it making it into the popular culture? Well, Big Bang Theory comes back, and I want to point out the James Webb model in the upper left. We're getting there, guys. All right, so all I want to say is, as popular as this machine is, I'm not sure the next statement can really hold true. We're going to need sound.
First time with a sense of hope. Because if a machine, a Terminator, can learn the value of human life, maybe we can too.
Left. I'll take your questions, but I can't guarantee I'm smart enough to answer them.
Can you hear me from this mic? No. This is not on. Hold on. Now, can you hear me from this mic? Yes? But hold on one second. How's this? So Kathryn, I'll pass the mic around and you can answer from here. If you can't hear, raise your hand, and I think I've maxed it out, but she can hold it closer. Sorry.
Kathryn, what did you say was the due date for launching this?
March 30th, 2021, but there have been several delays. So, yeah, they're evaluating whether it's still on schedule. The last I did check recently, it's still on schedule. The problem is with space stuff, one little burp, it's 2 years.
Hi, Kathryn. It's Judy. I want to follow up on that question. Was there also something having to do with lineup of this, and this? The reason that March 30th, 2021 was chosen out in space? Was there a spatial reason for it too?
Well, I think what you're touching on is there are astronomical reasons why there are some windows. And when we pick that date, truthfully, it should be a launch readiness date, ready to launch. But the fact is, ESA gets to weigh in on it. And if we say, hey, we want to go on March 26th because it's Kathy's birthday, they might say, we're actually launching a European mission, come back in April. So I can almost guarantee it won't be exactly that date, but they're supposed to be ready by then and good to go.
So what's the biggest problem in the James Webb shuttle that you have to face?
That's a very good question. It's a seriously very challenging mission. And I'll tell you the truth, when I was interviewing for the job, they called me up and they said, why don't you apply for this job? And I said, I'm an X-ray girl and it's an infrared mission. They said, yeah, just do it anyway. So I knew I wasn't going to get the job, but I was reading up on it. I figured I should answer. And here was the question. There are two big, scary things about James Webb. One was the money, and it's always going to be challenging to get support and be able to deliver on time and have the money you need. So it was a political problem. And the second one is the technology. It was so challenging. And when I originally read about it, I said, what are they thinking? They are going to deploy this thing? All the parts opening up in space 1,000,000 miles away at 40 degrees above absolute zero? I thought, are you nuts? And then, when I realized I wasn't going to get the job, I relaxed a lot. I thought, this is pretty cool. So the answer is, I'm really very nervous about the deployments, but I am assured that it has happened successfully like 2,000 times or something. So it should be okay.
What is the life expectancy of this project?
The goal is 10 years. In principle, we could tweak it along to 12 or 13. It's all going to be driven by the amount of fuel and how much gets used up in station keeping. And so, but Space Telescope is pretty smart about stretching their, using tricks. They'll all get together, they'll figure out the smartest tricks to do it. But just the same, that's the ultimate limitation. And it's not serviceable, really. 1,000,000 miles away, you're not sending an astronaut.
It looks like the foil is pretty delicate. Are you not worried about asteroids and random things?
Yes, very, very much so. And remember how it's 5 sheets, not just one? We've designed one. They decided to add 5. You understand it would be kind of a disaster if a particle went right through all 5 and allowed a line of sight direct onto the mirror. That would be a disaster. So they make 5, and they make them angled at different angles to each other. So if you get bounces or whatever, right? Okay, so it's a better chance. Yeah, but it's a good one.
Hello.
Hi.
My name's Kevin. How you doing?
Hi, Kevin.
Got a question about the exoplanets.
Yes.
Compared to the Kepler, how detailed are we going to get to the smaller Earth-like planets compared to the Jupiter-sized planets for detail?
Yeah, very good question, because this wasn't designed with that in mind, okay? And it's not the ultimate planet machine, and I'm going to mention that because it's a hot topic. Looking for a habitable planet is a hot topic. My institution did a study, and they designed a concept. You think 6 meters is large? 12 meters. Okay? They designed a concept that should unambiguously establish statistically how probable it is and whether it's out there, right? But it's going to be expensive, and I don't know if it'll fly, but it's a concept. So the question is, it's not ideal for that. The next one that I'm thinking of should be able to see the seasons change on an exoplanet. Yeah.
What is this is a technical question, what is the numerical aperture of that telescope, and what wavelengths is it diffraction limited to?
Oh, that's a good question. So it's supposed to be, I don't know if I can remember exactly. I may have to follow it up with you afterwards, or we'll have to go online and check. It's supposed to be diffraction limited at a particular wavelength. I can't remember exactly. I do know that the range of wavelengths here is about 5 microns to 25 microns over, no. It's 0.6 microns to 25 microns. 5 to 25 is mirrored. Most of them are in the near infrared. 0.6, so there's some visible up into. But I can't tell you exactly where the diffraction limit is, but it is such that at 600, 0.6 microns, it should be even doing as well or better than Hubble. Pretty good.
Hi, my name is Cary. You are seeing the telescope in the environment with a temperature of 40 Kelvin.
Yes.
My understanding is the universal's average is 2.7 Kelvin.
Yes, for the Big Bang background radiation is 2.7. It's not in thermal equilibrium. I think it's kept warm to some degree.
Okay. Thanks.
But I don't have much information on that.
Hi, my name is Tom Havens from Northeastern University. Thank you for a terrific talk.
Thank you.
I'm interested in knowing how can we tell we're seeing to the very edge of the universe?
That's a good question. So the trick is, here's the problem. You get the Big Bang, you get hydrogen to form, at which point the background radiation can escape when we get to 2.7 degree Kelvin background radiation, the cosmic microwave background. And then we get hydrogen, you're going to make a star eventually, right? So you make a star, but the problem is, as soon as you have a neutral medium, you can absorb any light and the star lets out. So none of the light escapes. So you have, for a period of time, dark ages. Even though stuff is going on, you can't see it. It's only when it starts to reionize the universe, sorry about the technical description, then the light gets out and you can see. Okay? So we won't see right to the edge, but we'll see as far as is seeable, right? We'll see what light escaped. And the way you'll know that, it's a good question. I think what you'll do is you'll be looking until you see the dark ages, okay? And you'll know when that era of reionization. I think that's how, but I'm not an expert on it. I can teach you someone who is on it.
The time's already in years from. Yes.
No, we actually think the first galaxies we'll see are, we expect the Big Bang was 13.7 billion years ago. The galaxies formed, the cosmic microwave background radiation, I think was released about 300 million years later. Yeah, okay, less than 0.3 billion-ish, I think. The first galaxies would have formed somewhere in there, and we will see somewhere, certainly farther than 13 billion. So maybe the first billion years of the universe is existing somewhere in there, is what we should be seeing. But, I'm not an expert in this. I looked it up on Wikipedia.
Good job. My question is there some central mystery about, say, the early universe that this telescope is designed to see? It's kind of like hunting the Higgs boson or something with the super colliders. There's something that this telescope will hopefully tell us about the early universe that we don't know now.
So that's a good question. I'm not an expert on that, but I think we don't actually know what came first. Did you get the first stars, which should have been massive and pure hydrogen, Did you wind up getting quasars? What actually, we're interested in what actually caused the reionization. Was it light from the stars or was it black holes forming? And we don't actually have that information of how quickly and how contemporaneously. So the truth is, though, like any great observatory, you're going to learn stuff you had no clue about. When they designed James Webb, they didn't really know about exoplanets. When they first went in, they didn't know about exoplanets. So it's a good thing we can see that, right? Yeah. Okay, so I can't answer that one, though. Sorry. Any better than that. Any other questions?
So you're fuel limited to 10 years. How opportunistic can you be? So, for example, we've heard that there's now a comet that's come, essentially it's an interstellar visitor.
Yeah.
Here you have this very large telescope. It would be very exciting. It has all of these spectroscopic capabilities. I think it would be very exciting to look at it if it would happen. How restrained are you in terms of opportunism like that? Is it something that has to go through peer review, in which case you'll miss it?
No.
My experience with peer review.
No. So normally you go through peer review, but you also have targets of opportunity. So often people will put in target of opportunity. If a comet comes this way, I want to see it. And so it's in the queue, so if one shows up. The other thing is you don't have an idiot as the director, and he has discretionary time, or she, whoever, in this case it's still a he, right? They go, what do you mean the comet's in the backyard? Look. So generally speaking, they do the right thing if they can and if they have time. Here's the trick though. James Webb is a big thing. It can move 90 degrees in an hour, which is not all that fast, okay? So it can track, and it also has the capability of tracking moving targets, which usually means Mars on out. It's too fast to be moving any closer than that. And so you got to make sure that this is trackable, right? That's it.
Hello. Other than solar power, is there any other power on the telescope?
Excuse me, is there any?
Any, like a battery or anything other than solar power, keeping it alive for 10 years?
I mean, we have fuel and we have solar power, but it's not no radioactive anything or none of that.
Hello. You had a micro-shutter array in your presentation that was rectangular, and you have a hexagonal mirror. How does that work?
So the mirror converges all the rays down to a point. Okay, it makes a nice point focus. So eventually the artifacts are going to go away. And what you want to do with that focused light is you then want to redirect it to the instruments. And so you shine it on the micro-shutter array, and the micro-shutter, I love that thing. It'll look out, it'll see a certain field of view, which is not all that large, but it'll be able to pick out some spots and open up the shutter and put a grating behind it. So it gets a spectrum from each of, say, 300 areas that it's letting light through. Now, what I like about it, of course, is I want it to, it's configurable. You can choose which shutters you want to open. You can open up a heart and put my initials in it, which I'm sure is scientifically justified. But it's really fantastic in that way. But the trick is you focus the light with the optic and then you redirect it to the instruments.
Thank you all so much for your patience tonight with our technology. Thank you to Kathryn for your patience and your presentation. Thank you to George for bringing speakers like Kathryn to us. This is honestly one of the favorite parts of my job, and I just feel terrible about the technology. I'm really sorry that it wasn't a better performance. However, I am very happy to tell you that LexMedia was here to record the event, and they did pick up good audio from all the mics. So in about a week or two, that video will be on their website. You can just search either for Cary Library or Kathryn Flanagan or James Webb on LexMedia's On Demand, and you can rewatch and hear anything that you may have missed tonight. Thank you again to everyone. I really appreciate it.